Excellent. So as I was saying, welcome everybody. I hope you enjoy tonight's presentation. It's going to be about 75 minutes long, do believe. And what we're going to talk about is flying at higher altitudes and some of the things that not necessarily all pilots recognize associated with V&E. You take a look at this picture right here. This is actually me flying in my glider up at 27,000 feet over New England. Has some impact on what we're talking about tonight, and you'll be able to see some of that a little bit later on. Now, most of us are flying in certified aircraft where we, the FAA, have done a lot to protect you from some of the dangers that may lurk at high altitudes close to high airspeeds on your aircraft, but that's not always the case in all aircraft, and that's what we will be taking a look at here tonight. So this is our monthly webinar, normally done by the New England FAASTeam. We tend to do it on the last Tuesday of every month. In the Bradley FSDO, we have Dan Carter and Rob Leonard. Rob cannot be with us this evening due to a prior personal commitment, but we do have Dan Carter. Dan, if you just want to say hello so people know your voice.
Good evening. I'm looking forward to this webinar. I saw the some of the preview stuff on it, and it's going to be very interesting. So buckle up. It's a lot of information.
Yeah, that's probably a good way to put it. And as that old commercial goes with what you're getting tonight, you know, I am not an aeronautical engineer nor an aerodynamicist. I just play one on TV. From the ops inspectors from Boston and Portland, Maine, are myself and John Wood. John there in the back, I up in the front. John, you just want to say hello so everyone recognizes your voice?
Sure, you bet. Welcome aboard, everybody. I'll just echo what Dan said. There's a lot of information. This may be one of those webinars that you actually want to watch the recording after you watch the live version, just to make sure you absorb everything that you're going to hear tonight. So welcome aboard.
Buckle up and keep up, guys. Right? We'll have fun tonight. It is, but there is a lot of information. And, you know, as I've taught this over the years, in some of the different classes I've taught, I've had many students and many pilots that have been flying for years. Like, I did not know this. Whoa, this is some really interesting, neat stuff. And that's what I hope you come away with tonight. We do have airworthiness side, like Rob Leonard out in Bradley. We have John Bell. He's not able to join us this evening. And here's what we're going to hit upon tonight. We're going to talk about V&E primarily, but some associated airspeeds with that. We're going to be talking about true airspeed quite a bit. And the big subject we're wrapping this all around is what's known as flutter. And that is an aerodynamic condition that can be very detrimental to your airplane's health and your health. We're going to talk about general air or GA airplane, general aviation airplane certification. And we're going to take a peek at the old CAR Part 3, FAR Part 23, not once, but twice. And there's a good reason for that. Talk a lot about the margins and protections, maximum operating altitudes. We're going to talk about gliders in V&E, take a look at a different type. And we're also going to talk about experimental airplanes in V&E. It's appropriate to all of them, but gliders and experimental airplanes don't have anywhere near the margins and protections designed into them that standard airworthiness certificated airplanes have. We're going to talk about modifications and things you need to consider that you may not have considered in modifying an aircraft. Talk about a few other high true airspeed issues that can occur. And last but not least is safety planning consideration, taking all of the above into account, including a little bit on pilot certification. So you take a look here, we're probably all familiar with this, an airspeed indicator. And if you're like me, you probably have been flying long enough that you recognize an old style airspeed indicator versus the glass panel that we have now. And all of these airspeeds that you see on this are given to us as indicated airspeeds, i.e. they really don't change as we change our operating environment or the altitude that we're flying at. However, there is one speed, and that's the red radial line, VNE, that does change. It has both an indicated component to it and a true airspeed component to it. And I'm going to point out, I don't know if this is something that people are familiar with at all, but many airspeed indicators have the capability to indicate the true airspeed on them with some dial function that they have, which is probably a surprise to a lot of people. Some other speeds associated with this that you just do want to be aware of. They may or may not appear on your airspeed indicator, but VNO, which is maximum structural cruising speed, we'll be taking a look at that. That's shown right at the start of the yellow arc of your airspeed indicator. We're going to talk also about design cruising speed, which in almost all airplanes is equal to or very, very close to VNO. It's actually a speed used in the design of aircraft and the certification of aircraft, but it tends to equate to VNO. I want to talk about maximum dive speed, which is actually used in the certification of VNE, along with maximum demonstrated flight diving speed, which again is used in the certification process, but there may be times within the testing that they find out, we can't quite get as high of an airspeed as we want. So this is the max that we've been able to reach. So you're probably familiar, I'm not going to spend a lot of time on this, but we have different airspeeds that we talk about. Most of us are familiar dealing with indicated airspeed. And if you go back to your certification days, you may remember you were taught to figure out calibrated airspeed at some point in time. Sometimes you'll see that your performance charts will be based upon calibrated airspeeds, even though you're looking at indicated airspeeds. And most of us know, thankfully, we do a good job at designing aircraft. There's usually not significant differences between those. Most of you probably don't recall or may not remember well equivalent airspeed, which is designed for at higher speeds when we end up dealing with the adiabatic compressible flow. Basically, like think of it as a wave building up in front of the pitot tube or that sort of thing, but that tends to happen at much higher speeds. Generally below 200 knots, it's a non-factor, non-event. So most of us are flying GA aircraft at speeds like that, so it's not a big deal. But we always have had an interest in true airspeed. And the reason why is we like to go places fast. And as a result, we've tended to go up fairly high. And even in relation to density, altitude, takeoff, landing performance, we've talked quite a bit over the years about true airspeed and the impact that that has ultimately on our ground speed. As we get less dense atmosphere, the molecules spread a little bit further apart. And just to give you a little bit of an idea of what that looks like, I'll leave the old ground speed up to you. You probably deal with it and care about it enough that you know what that is. But if we were to look at an aircraft and we're looking the 150 to 225 knot range at different altitudes, and this is all standard atmosphere, at 150 knots at sea level, basically everything is equal, calibrated, equivalent, and true airspeed. But you go up, you'll see like at say 18,000 feet, and I'll use the little pointer here to make it easier, 18,000 feet, true calibrated airspeed of 225. What happens is our equivalent airspeed as we go faster and faster and faster and approach, Mach 1, ends up decreasing, but we see big differences in our true airspeed. And if we're in an aircraft that has a VNE that's pretty darn high, or fairly low, we end up in the situation that our true airspeed can get way above VNE and have an impact on us in the flutter protection capabilities of our aircraft. Now, what is awesome is today we have bit more modern aircraft, not quite as modern as it used to be, but I used to fly the Eclipse here quite a bit. And that was different because it was one of the first aircraft out there that instead of giving you an indicated airspeed, because it had a computer on board and it could calculate, you know, the calibration of the system into it. And it also knew what the outside air temperature, pressure, and all of that was, is everything displayed to you as the pilot was given to you in knots equivalent airspeed. You didn't have an indicated airspeed in the aircraft. It always was displaying knots equivalent airspeed. And even some other aircraft have done that. When it's not indicating in Mach, is the space shuttle indicates in knots equivalent airspeed. Now, you know that, and you know all that other stuff, you pretty much also know your true airspeed. And that's what we're seeing a lot on panels today. You know, now you look at something like just this Dynon Skyview, and a lot of experimental aircraft out there can be put in certified aircraft too. Not only do you get your indicated airspeed, but it is able to determine the wind's loft, all of that, and temperature and everything else. So you get knots indicated, you get not true airspeed, and oh, we're going to give you ground speed also, so you don't have to do that mental gymnastics with it. Now, we're talking about all of these airspeeds because what I was saying is there's a part of V&E that we always need to be thinking about in terms of the true airspeed, is how fast it's going through the atmosphere and what the thickness of that atmosphere is. And when we talk about it, we start thinking about flutter. And flutter in an aircraft, it can be thought of as similar to the flutter that you end up seeing on a flag. However, flutter is not dependent upon the dynamic pressure to it. It's more directly related to the true airspeed, the velocity passing by. And what you want to do is think about it in terms of the thickness or the viscosity of the medium that it's in. Is the thicker the viscosity, the more dampening effect that it has if it gets displaced, and it will thin out. Think of it this way. You know, we take a flag and we're in the basically no atmosphere of the moon. We stretch it out, you know, and let it go. And it ends up in the solar winds fluttering with absolutely almost zero speed with it. You put the flag up in the air, and at 5-10 knots of wind, it's out straight, nothing really happening except maybe a little ripple on the end. But you then bring up to 30 knots where it gets excited more, it starts to flutter around. Now think about, like, if you put the flag down in the water, how fast you could go and how difficult it would be to flutter off side by side like that. And even more difficult if you put it in something like oil. And that's the same issue we have with the flutter aspects of an airframe. Usually we think of it in terms of elevator or aileron on it, but it can apply in other places. And it's the dampening effect associated with the viscosity of what is around it. And when we go up in higher altitude and the air molecules are much, much further away, there's less dampening effect on it. So you've seen the atmosphere before, and you know, we fly in small general aviation airplanes, and we're always right down here at this very, very little bottom part to it. But what is important, which plays a big factor on the density of the air, is pressure. And if you look at just the lower portion of the atmosphere, like the troposphere that we're in, you know, you take a look at this chart and it shows you a few things. One is you'll notice that the rate of change, you can tell because the squares are near the same size. Down at lower altitudes, the rate of change is about the same. You look higher where the boxes get bigger, the rate of change is much more slower, spread out. It tells us, like we already know, a lot of the atmosphere is basically put down in the lower portions of it. you know, so we take a look. Most of us are flying at 10,000 feet and below. And, you know, we know sea level pressure is the 1013.2 millibars. Down here, where'd my marker go? There we go. The 13.2 millibars or 14.7 psi or the 29.92 inches of mercury. We also know that it tends to decrease about 1 inch of mercury per 1,000 feet up to about 10,000 feet or so, which is about a half a psi or 34 millibars. But what it is 75% of that atmosphere pressure is down at 10,000 feet below, where we always end up flying. You know, you take a look at 18,000 feet, which is about the highest most of us will ever fly if we have some supplemental oxygen in our airplanes and stuff. We're down to half the pressure of the atmosphere. You know, so we're seeing significant differences in pressure and density of the air just in that lower portion from 0 to 18,000 feet. Significant changes. And then, you know, not all of us have the opportunity, but this is the case for a lot of GA, is, you know, some of us have the opportunity to fly up to 25,000 feet. And then nowadays, 28,000, even in some older turboprops and other pressurized aircraft is the limit. And even some newer turboprops, just because of RVSM airspace with it, is that's the point that we only have a third of the pressure. You know, so where we operate, we see dramatic differences in the pressure in the atmosphere, which equates to dramatic differences in density of the air that we're flying in with small changes in altitude. You know, it also gives you a little bit of an idea as you see how little pressure change there is up at the higher portions of this, and why RVSM equipment has to be so sensitive and can be so expensive. You know, before we had RVSM, because there was so little pressure change and being able to measure it, that's why we used to separate aircraft at 2,000 feet. And we just needed really, really good modern equipment to be able to do it at 1,000-foot intervals. Now, a little side note to this, just to give you a little bit of an idea of, you know, how dramatic it can be. And I got to hand it to the people that put this together. You know, Ingenuity, that little Mars helicopter that's flying out there on Mars. To give you a comparison, they think the thickest part of the atmosphere on Mars is equivalent to being here on Earth and flying at 115,000 feet. And they were able to design a helicopter that flies at that altitude and also doesn't break apart because of flutter. So, you know, I really got to hand it to those folks. They really did their research and have done a good job. Now, what is it that's the danger? Here's a little simple diagram of what happens as you increase in velocity with this, and I'll let this play. As the velocity continues to increase, you finally get to a point where an aerodynamic resonance starts to develop, and you end up with turbulent flow. And as that comes back and catches onto a control surface like an aileron or an elevator, it starts to flutter, whip around in an uncontrolled manner. You know, maybe computational fluid dynamics, maybe now they can figure it out, but 20 years ago it was still almost impossible to be able to do. And it gets out of control and ultimately can lead to structural impact on your aircraft. And when we design for V&E, we're designing in kind of two senses. One is the structural integrity is enough that the air hitting the wings and all of that doesn't break it. And we got to think about it in our aircraft on all sorts of things. It's not just the wing, it's just not the tail, but it's everything we kind of have hanging out of it, whether it be steps, gear fairings, antennas, probes, vents, all of those things. We need to design that they're going to stay on the aircraft and not break off when we accelerate to as high as V&E. But we also need to design for flutter, which is self-feeding, potentially destructive vibration, where the aerodynamic forces couple with a natural vibration mode to produce the rapid periodic motion that gets out of control, as we're looking at here in this diagram, and we end up seeing. So that's the two things that we're kind of thinking of in a broad sense at that level. And if you haven't seen this before, this is models in a wind tunnel, but the same thing can happen to an aircraft. Here. And you can see, you know, the vibration that starts to occur as the speed increases and how, you know, it ends up moving around. Flight controls would be moving out of control and moving opposite directions that you would want them to. It ends up involving twisting and torquing the wing or other parts of the aircraft, and ultimately it leads to destruction. And it not only happens or can happen on the wing, but things on like the tail here too, is it gets up there quick. And you may have even seen the video of the Tacoma Narrows Bridge in the past. You know, many of you are probably at my age where at least you saw that video in school at some point in time with it. And, you know, it gives you an idea of what it looks like. Now, what impact it has on us as pilots, if we end up flying too fast, probably, especially in certificated aircraft, that would be exceeding V&E. You know, what it would end up doing to us, it likely is going to break up the aircraft almost instantaneously with it. And here's just a little example. It does occur. This is a quick little search I did on the NTSB in relation to it, where I checked for probable cause and they had flutter listed in it. However, I really do strongly suspect and know that it has occurred in many more accidents, that it just isn't listed in the probable cause. You know, things where they talk about a loss of control, structural failure in flight due to excessively high speeds. Well, what started to cause that was flutter that probably occurred on the airframe. And this is just a couple pictures from an accident that I'm familiar with, that, you know, the aircraft did experience flutter with it. Many times it's fatal, but not always, thankfully, given the circumstances, and we'll talk about that a little bit. But here's some remnants of an aircraft. This was a glider with this. And what you're looking at right here is the main wing spars where they attach together with the large pins in the fuselage along with the wing roots. So this is the main wing spar here. You know, the wing skins and all of that would be attached on the outside of this. This is what's inside the fuselage, the main wing spar pins right here where they integrate. And then this is the wing root material that would be over it in this area. And this is what the pieces look like after they found them on the ground. Here's what the wing spar, you know, basically a solid block of carbon fiber, which is one of the stronger materials out there, ripped apart. And then, you know, the scary part to this is the fuselage. And if you remember that wing spar butt end, that large block I had talked about, this is where it got pulled out of the fuselage, ripped right through the roof of the aircraft when it exceeded V&E and experienced flutter. Is the wings basically, you know, ripped off, came ripping right out of the top of the aircraft, bringing the spar with it. And the scary part is the pilot's head, as that occurred, was right about here in this portion of it. So it ends up, you know, being a very interesting accident. This one, the pilot actually got away with just minor injuries. Believe it or not, most of the injuries were associated with the landing after parachuting out than anything else. So most of our aircraft in general aviation fleet, believe it or not, are certified back to our old rules from the 1950s. You know, way back under the old CAR Part 3. And believe it or not, we knew enough about flutter and vibrations then that we had most of the rule set developed fairly well. Basically here's what the regulation associated with it had. And what basically happened is we moved from the old CAR Part 3, you know, all your Cherokees and all of that are probably certificated under CAR Part 3. The Cessna 172s up until the R model were certificated under the old CAR Part 3. What has happened is we've just added to that a little bit over the years as we've improved with the Part 23 certification. And we even learned some really interesting things like what's known as whirl flutter on multi-engine airplanes and stuff like that. Had design criteria associated with it. Also, you know, our newer aircraft, which are designed to Part 23, and I'm purposely have here the old Part 23, and we'll get to that. But just to give you an idea of what we end up doing in the certification process in a thumbnail sketch is basically you design an aircraft and we say, you know what, you got to design it so we have what we call a VD or design dive speed with it. And we must design it so that we don't think from our computer modeling engineering slide rules that we're going to have any flutter unless we're at least 20% above VD. And then correspondingly, VD, we want to be at least at a minimum 1.4 times VC on it. You know, and then what we do is we pay a test pilot. We say, hey, what we want you to do is go fly this to what we calculated. We don't think it's going to encounter flutter unless you're 20% over that speed, but you need to go prove it for us. Can you do that? And you do that. Test pilot comes back and says, yeah, I flew it up to there, all good. And then we, the FAA, get out with our little red pen at this point in time. And we decide we're going to put a little mark on the airspeed indicator based upon that. And that's where we start putting in the airspeed limitations. We say, you know what? We're going to tell you now V&E is 0.9 of that VD. So what we've done is somebody has tested one aircraft or two aircraft, maybe three at some point up to what is the equivalent of about 110% of V&E. They've gone just a little bit beyond, and that's what I mean. It's just a little bit. It's not a lot there. And we say, here's kind of the criteria associated with it. So we're going to put V&E in this spot because we designed it for a 20% buffer over what they tested, and we've actually tested it hands-on with a 10% buffer. So we think it'll be good with that. And then we end up setting it, and ultimately the cruise, which is used in the Part 23 regulations, which has to be so much the square root of the wing area and so forth and so on, basically ends up becoming V&O. V&O, the start of the yellow arc, almost always is the same or very, very close to it. There may be some variations due to nuances in the regulations and the calculations. So basically, we're designing for these gust loads, that sort of stuff. This is what we're planning on and designing to this cruise speed. Now we're going to take this cruise speed and say, we're just going to make sure we have design criteria up to this dive speed and a little bit beyond for flutter. And then we're going to set cruise as V&O and 0.9 of the dive speed as V&E. Test pilot, go do it. And that's why they get paid the big bucks. But a few things to think about in the test conditions. And, you know, part of this is playing the captain obvious is the airspeed indicating system should be calibrated. Got to do that first. You know, you don't want it reading off by 10% when that's the margin you're testing to. You know, you got to secure everything in the aircraft and stuff. Yeah, because it can get, this is one of those high risk tests that test pilots get paid the big bucks for. And then this is an interesting one is we do purposely say to an applicant for the certification of the aircraft, you know, control surface and stuff should be balanced to the most tail heavy condition in the free play near the limits, you know, basically worst case condition. So if you say, you know, it's still okay within 0.2, we want to test it to 0.2. But you need to know that's still within limits. We're not talking about controls that may have worn out a little bit or cable stretch that's beyond limits. You know, it's still being tested within the limits. And what's also interesting is our guidance says it should be checked at 2 places, at least 75% of the service ceiling, and then also one of what's known as high dynamic pressure, i.e. a lower altitude, but you still want to be able to bail out, Mr. Test Pilot, if you have to. So most of the testing tends to be done around 9,000 feet. And for our small GA aircraft, not the jets or turboprops, but our small GA aircraft, that's about the whole area that they're tested in. There's not much more because most of our aircraft don't have significant changes in altitude. Some do, you know, we can get up to 20,000 feet in some, but most that we're familiar with, that's not the case. So I talked about the old Part 23. If you did not know, we, the FAA, completely revamped Part 23 year and a half, 2 years ago, maybe even 3 now with it, and things change. Basically, what we now say to an applicant designing a new aircraft is show me. And instead of having a lot of set criteria, we basically say, you know what, it can't flutter, we can't have roll reversal, we can't have divergence, all of that stuff at high true airspeeds. You know, and it needs to be structurally strong enough for any configuration, blah, blah, blah. Show me that you can do that. And that's how our new regulations, our new Part 23 is kind of set up. Now, I'm not in that part of the FAA. I don't work in that world. They probably are still using a lot of the old guidance for references and things like that. But we have changed it significantly, and there's a lot of changes coming for the certification of aircraft from this point forward. So you're seeing brand new aircraft. That's what it's coming down to, is we are now saying to the applicants in a simple sense, you know, the old classic Captain Obvious, show me that you're able to do this. We're not telling you how you have to do it. What we want you to do is show it to us. You know, so what happens is we end up having margins that are built into certified aircraft, but you need to recognize in this arena associated with flutter, as you increase in altitude, that they are getting smaller and smaller and smaller. They should be large enough that you have, you know, plenty to keep you safe, but you got to also recognize some things is the aircraft we're flying aren't young anymore. You know, it's rare for even me in my 50s to fly an aircraft that's younger than I am. You know, and we'll talk about that a little bit more. We also have design things in it is got added in over the years, you know, hey, guess what? If you lose a trim tab, the aircraft still can't flutter. You need to prove that in your design. So, you know, we have built in buffers as time has gone on. However, that all being said, and if you've been flying for a few years or no history, we have dealt with flutter in some certified aircraft. And if you're curious, this is a NASA video. Quick, you can see flutter starting to develop in the stabilator. We've had issues with the stabilators on other Comanches, the V-tail Bonanzas. Most of these that we've ever had issues with were certified way back in the 50s under the old CAR Part 3. Now, if you're not familiar with that, that was a twin Comanche test that was done back in the 60s. And a little history note, guess who the test pilot of that was for NASA? Was Fred Hayes, who you may remember as the command module in Apollo 13. And guess what? He had said he had never been as afraid as when he was doing those tests, and they did start to experience some flutter. So, you know, interesting little side note there in the realm of aviation history. Other parts to this that we end up doing, you know, is how is it that we design an aircraft or tell a company to design an aircraft is probably a better way to say it, with protections. And what we do is we're really looking for some things when we design the wings and the ailerons. We're looking for, you know, the torsional flexibility, the aileron balance is super, super important. You know, if you fly old Piper Cubs and only fly below 100 knots, or even some older gliders like 126s and 233s, you'll see there's probably not anything there for the balance because you're just not getting high enough or fast enough for it to be a factor. But the faster and faster that you go, the higher and higher that you go, the more and more important it is with it. And, you know, in the elevator and rudder, we look for the geometry, the stiffness, and the mass in those features that we design in to pretty much keep them as stiff as we possibly can. We also have kind of changed our policies a little bit, I guess is the best way to describe it, is we also have started issuing in years past, this is not service ceilings, but maximum operating altitudes. And you even see it in the smaller GA aircraft now, is you'll find in section 2 in the limitations, you know, a maximum altitude that the aircraft is allowed to operate up to, taking many things into consideration, but the flight and the structural components to it, accounting for flutter. So you go out and buy a new aircraft, you might think, oh, I could fly it up fairly high. Well, that may not necessarily be the case, and it may not, even if it's capable of doing it. And basically 25,000 feet is a limit unless you have pressurization and also certain things above and beyond that. A good example is the, the Cessna pressurized 210. If I recall off the top of my head, the maximum operating altitude of that aircraft is 23,000 feet because it doesn't meet pressure differential requirements and all of that, a Part 23. So you can even have pressurized aircraft that can't go above that. But here's just a few examples. As I was saying, most GA aircraft have been limited to at least 25,000 feet and below in today's world. And that's because of Part 23 certification limits on masks. Many times you'll also see to 18,000 if it doesn't have an oxygen system with masks. There are some, like the old pressurized piston Duke was originally certificated 30,000 feet, but when they got the STC for the turbine conversion on it, they lowered it to 28,000 feet. The Cirrus, which you think, oh, geez, especially the turbocharged versions, which are great and can go fly. Well, the non-turbo version Cirrus has a max operating altitude of 17,500. The turbo version is allowed to go up to as high as 25,000. Again, that goes back to the masks and not pressurization. But Technam, they've come out with new Part 23 certified aircraft a lot lately. You know, their P2006T, which is the little 4-seat twin trainer with twin Rotax 912s on it. Maximum operating altitude, although it's capable of going higher, is 14,000 feet. That's as high as you're allowed to fly it. It is a limitation. The P212, which is what Cape Air is starting to use, has a maximum operating altitude in the type certificate of 13,000 feet. That's the maximum it can fly. It can easily fly higher than that, but 13,000 is what its limit is. And then this is a picture here of the 210, but the 210 is certificated depending upon what engine you have in it. The IO 360, you're only allowed to go up to 12,000 feet. So getting across the Rockies is going to be pretty darn difficult. The IO 390 is 14,000 feet, but the TDI diesel in it, turbocharged, is up to 18,000 feet. So what we know so far, and this is just focusing in on certified aircraft, is we now know what gangs up against us as we go higher. We go faster, but we are dealing with a lot less anti-flutter dampening, which we've been talking about here, and how we have decided that the airspeed indicator lies to us. It's not going to be reading right. As we see, our true airspeeds are much higher than our indicated airspeeds. And for flutter protection, it is true airspeed that we need to know. But unless we're paying particular attention with a true airspeed indicator, mechanical one that we're adjusting and we know how to adjust it, or we have a well versed glass panel, we're in a condition that we probably don't have that information available to us. Yeah, and that's what we really do need, is an awareness of the true airspeed when we talk about flutter. Now let's talk about gliders. You know, glider pilots are goofy, and so they've figured out how to handle this with the long, flexible, elastic wings. Yeah, some of them have, 30+ meter wings, really huge ones. Like this is the Nemeda glider, if I'm pronouncing it correctly, and on a YouTube channel by Stefan Lager, you can see it fly and learn a bit about it. And then there's also another glider out there called the ETA, which is similar. Also, we've been looking, you may have heard about the Berlin project that's going on, that's breaking altitude records. Last I knew, there were at least 79,000 feet. It's an unpowered glider, but it's still flown higher than the U-2 has been able to fly at this point in time. And they're trying to get to 90,000 feet, but this is one of the huge issues that they're dealing with. And believe it or not, what they have built into the wing is what's known as flutter exciters. And you can find this videos of it on their website and stuff, that provides telemetry data that before they actually are going and breaking a record, they're testing the conditions and testing for the possibility of flutter in their aircraft. And gliders tend to be aerodynamically slick. And guess what? Even though we have certified gliders here in the US, basically almost every glider now is certificated to EASA CS22. It's been since the 80s, I believe, that the FAA has been using that criteria on the certification of gliders. And there's similar things in there, but not necessarily so similar things. And this is where you start to learn. Gliders have the benefit of having dive brakes, and in their certification, at least on a 30-degree angle, and depending upon what it's capable of, 45-degree angle, and not be able to exceed V&E with the dive brakes all the way out. So you can be at a fairly nose-low attitude like this and still not be able to exceed V&E. And believe it or not, like you see here, the Schweitzer 134, with its dive brakes out, has terminal dive brakes that it should not, and I emphasize there, should not exceed V&E 90 degrees down with the dive brakes out. So it has kind of that protection capability to it. And then they also go in to this issue, because gliders, unlike airplanes that are certificated that have maximum operating altitudes, usually do fly at drastically significant altitudes given certain conditions. And, excuse me, and what they basically say is, you know what, if you're going to be flying this at different altitudes, and because we have these long elastic wings that have, you know, looks like more capability to produce flutter, if V&E is going to reduce with altitude, you need to have a placard in the aircraft for it. And what's also a factor in this is where the testing altitudes usually occur. Within the certification world, most of the testing occurs at 500 meters and 3,000 meters in gliders. Not beyond that, not some in between, but it's usually at those two altitudes. So what ends up happening in gliders where you have long wings like this is you usually find what they have is a pretty low V&E. And that's because you have the long wings and the impact on the structure and the flexibility on it. And that's especially the case without the more modern materials of today. I use as an example, this is a picture of my glider, which was, you know, the hot racer in the very early 70s, but the V&E on it is still only 119 knots. It's not that fast with it. And most gliders do have graphs where they adjust V&E for altitude. This is a duodiscus XL, which you can see. Let me get the marker back. You know, at 9,000 or near 10,000 feet, you're seeing your V&E has dropped about 5 knots, but it's not uncommon. A glider like this will fly up to 18,000 feet quite often, and you're seeing, you know, 25 knot decrease in V&E. And even if you have the capability and get up 30,000 feet plus, you know, you're now looking at close to 50 knot decreases in your V&E. What is the limit that you're able to fly that glider without experiencing the detrimental effects of flutter? The pipistrelle sinus motor glider, same thing. I know this one, actually, the certification tests were all done at lower altitudes. So even as low as 3,300 feet, you end up seeing, or 1,000 meters, you see the V&E is starting to drop off. And even some gliders, I use mine here as an example, does not have that. But if you're going to be flying at higher altitudes, you know, you definitely want to do it. And this is right off of my own personal checklist. Is you see V&E 119 knots, but I have calculated, working it backwards from the V&E in true airspeeds and standard conditions at those altitudes, what I have is my recommended new V&Es that I fly that aircraft at. You know, want to make sure that I do not become one of those statistics where I've experienced flutter in a glider. So you look at that, a little bit scary in what happens, and that is exceptionally mild, is that can accelerate very quickly to a point that basically the aircraft self-destructs. Anytime that you start to hear some buzzing, feel some shake associated with that, especially if you're flying at higher airspeeds, is, you know, you want to reduce the power and throttle back. And I've compared and contrast now gliders and certificated airplanes, but the world that this is probably most important to, that people don't realize, is the experimental aircraft world. And that's primarily the experimental amateur built world. And the thing to realize there, it's the wild, wild west, and it is up to you. You're your test pilot on how you do it. And here's a few things just to kind of note with it, is if you look at our FAA guidance on flight testing, we actually go the other way and we say, you know, if you build a kit or whatever, and the manufacturer has said V&E is some speed, let's just take 200 knots for whatever reason, we don't recommend flying over 90% of the recommended V&E by the designer in the experimental world, because there's just so many different things. And also because it's not checked, not certified, we just don't know. It's up to you to determine that. And we don't want you to risk yourself in an aircraft in that type of situation where you're going to hurt yourself with it. So, you know, our general recommendation is to only test up to 90% of the planned V&E. You know, a certified aircraft, we're going 10% over V&E. Experimental aircraft, our recommendation is to only go to 90% of it. And that's one of the things. Experimental amateur built, it can go a wide gamut. It can go from, you know, basically putting together the puzzle pieces of a kit that many others have built before you, to you technically can design your own aircraft and build it yourself and test fly it yourself. You know, but that's one of the benefits of buying a kit aircraft if you're getting in the experimental world, and also buying one, you know, from a reputable builder that has, you know, aeronautical engineering staff that have done this, been kind of independently tested by many other builders before too. And of course, I always will emphasize, if you are getting in the experimental aircraft world, which is a wonderful world to be in, home built kits, but make sure you're getting as much as you possibly can in the resources available to you from EAA, because you can even modify in the experimental world and do some stuff. And I have seen some really crazy things out there. Is, you know, if you're going to go into experimental modifications, you got to really think, are you an engineer and have you done the calculations? I've seen a couple things and I've asked about the calculations and had truly engineered, well, I thought it would work. Well, you know, it's probably not the best way to approach it, you know, and think about it. Has it been tried before? Is it worth it too? And last but not least, this is something, you know, and all of us around the world have, in accident investigation, have kind of picked up pieces because of this. Really, are you ready? Do you want the modification that bad that you're willing to become what I would call an old school experimental test pilot? You know, somebody out there that does push it to the limit. And I say this partly jokingly, but there's a lot of truth in it, is think about Edwards Air Force Base. All the streets are named after dead test pilots. You don't want to be one of those test pilots that has a street named after them. And if you're flying in the experimental world, you probably know this or should know this, and probably expect all your friends that fly experimental aircraft to know this. Not only do you have the experimental airworthiness certificate, which is usually pink, doesn't have to be anymore, but usually is for most of us, but attached to that is the operating limitations for experimental aircraft. And they end up having to have attached to the airworthiness certificate. And you'll see in pretty much all of them, the largest block of print is if you're going to modify the aircraft, that puts it back into what's known as phase 1 of the flight testing. That's what you want to be aware of, is you're going to have to go back. You're going to need to notify the FSDO. And boy, if you're putting in a bigger engine, changing the propeller or something like that, there's going to be a lot of questions asked about this, because it can have an impact on what your safety ends up being as a pilot. And if you're thinking about it in the regular world of standard airworthiness certificated aircraft, because we do get people all the time that contact us at the FSDOs, call up and say, you know, hey, I know I got a Stinson 108, but I want to put a 285 horsepower IO 540 in it. you give me a logbook endorsement for that? That's not the way that really does work, because there's a lot of safety that goes into the planning on that. And if you want to change something like an engine or whatever, you probably want to look at, you can Google this, the major repair and alteration data approval. It's a guidelines that we have for our inspectors, say, you know, hey, if somebody wants to do this, this is the process that they probably need to go through on it. And, you know, if you're going to change the V&E of the aircraft, operating altitude, service ceiling, engine prop, CG limits, we're going to increase the power by 10% or more. All of those things require an STC. You know, they're not going to be done under a field approval. They may have been 30 years ago, but it's not going to happen today. You know, is why this is one of the reasons. It's not the only reason. It's one of the reasons. So, and then they are out there, and some of them are absolutely terrific. I've flown a bunch of them, not this particular model, which is a little bit of a Frankenstein from back years ago. But, you know, many piston-powered aircraft do have turbine engine conversions. And one of the things people end up asking is, what happened to that yellow arc? You know, what happened to VNO? Well, that now became VMO, and it's now your new red line. The yellow arc goes away in the turbine-powered aircraft. Why? Because we know the climb capabilities and the higher altitude capabilities are going to be there. So we take that back down to V cruise, especially as you get up into higher areas, true airspeed wise, that you really are taking what buffer limits we had in the design down, 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 and getting there so close that when you convert over to a turbine conversion, that's one of the things with the STCs you're almost always going to see is your new red radial on your airspeed indicator becomes what used to be the start of the yellow arc. That's going to be your maximum speed from that point forward, because you just have eaten up all of that buffer towards flutter, being able to fly higher and faster. Other issues that we're not talking about significantly tonight, but can end up occurring with this is divergence, which basically, you know, is a twisting moment that can end up occurring at higher speeds, which could be there. In fact, you see this start to happen. It has a factor on the next thing we're going to talk about, but you know, all wings have washout typically so that they stall in on the inboard portion, i.e. there's a little bit higher angle of incidence on the inboard portion versus the outboard portion. And we see this in gliders is as they fly faster and faster and faster, you reach a point, and this has happened in the past, more modern designs do much better at this, where the wing tip, because it's at such a low angle of incidence, starts to become a negative angle of attack. And you end up in this circumstance where the wing is now starting to twist significantly downward. And you end up in this circumstance where as you're flying, I don't know if you can see this and I can't do it much, but as you fly at high speeds, your wing starts to bend the other way around, which is not good usually. And then as you end up doing that, you can also end up with a circumstance of control reversal, where actually because of that very low angle of incidence is you might want to roll the aircraft, you know, say in this direction and put this aileron down, but because you're at basically a negative angle of attack, even though you put that aileron down, it rolls opposite the direction that you were planning on. So that's something to be aware of at very high speeds. And again, our standard certificated aircraft all have designs to keep you from this area. You know, that's what V&E is. It's to keep you protected from this. But as you get into other stuff, maybe like gliders, maybe like experimental aircraft, you may not know how much of protection there is. And this is where, you know, you can start to ask questions of yourself in the flying, whether it's certificated aircraft, experimental, gliders, whatever. What is it that you can do to improve your safety? And there's a lot of different things. One is the rigging on your aircraft. And this is an issue with our general aviation fleet as a whole. 172, when was the last time that your controls were checked? One, for proper deflection, that they meet the standard, the type certificate data sheet for how many degrees up and down that they go. And also that on the flight controls, they're checked for how much free play there is in them. A lot of our aircraft are 50, 60, 70 years old and have never had that done. And, things wear out, cables stretch, pulleys wear down, all of this. And that's something, that you really got to be thinking about, is that's another way that you may not realize it, but we as a whole within aviation, flying the much older aircraft, have probably eroded away some of our margins. And if you're flying up near V&E in that yellow arc, you got to start thinking about that sort of stuff. Modifications, planned or unplanned on it. I've seen things done on aircraft that should not have been done, that owners have done, so forth and so on. And even certain things, most manufacturers don't allow stop drilling of cracked control surfaces for some of the same issues we've been talking about here today. And even some stuff that we do allow. We have a letter out there in relation to external camera mounts that basically, I'm paraphrasing it, but says, we, the FAA, we're not going to worry about it unless you really do something wrong. Then we'll worry about it. But I put this picture here as a Mooney that, the pilots like to fly fast. They're slick aircraft. They can accelerate faster than most others, like Cessnas and biplanes and all of that. And I have saved this picture. Here's somebody that put a GoPro camera mount out right on the very end of the stabilator. That puts weight in an area on something that we see that can have some movement. The Mooney's also with the tail, as the trim, as it gets older, it can get there. We saw the Twin Comanche video a little bit earlier with it. I also look at it and I look at where it is in relation to the balance tab here aerodynamically, and also the control weight. And last but not least, if you do go high speed in it, it's a higher likelihood it's going to break off. And where's the most likely place it's going to go and get caught if it gets caught on the aircraft is right there at the elevator control. So, you're doing modifications. You got to think about these things is what I'm getting at. Balance weights are so important. And I've seen Cessnas where they're missing. People have drilled into them, taken stuff out, all of that, and the external devices I was just talking about. Here's some other things, just a quick list. Always doing the proper pre-flight, checking your mass balance weights, the integrity of it. If it's got play that it should not, it is dangerous. You think about, or potentially dangerous. Planning your descent. A lot of us like to go fast, like to get to our destination, but you really got to think about it. Is it worth getting into the yellow arc? Is it really only in smooth air? Is it worth pushing it close up to V&E? Are you better off starting your descent a bit further out if you can, than in closer and pushing the nose over for a very, very high speed? If you got some chance of turbulence, keep it below the yellow arc. This is even true without the flutterers. We're talking about it. And at the end, I put in where this comes from, an article from Australia, which is good. One of the indicators to flutter usually is a hum or a buzz that starts at high speeds. If you recognize that, that's your first clue to you could be starting to experience flutter. Slow down immediately. Reduce the power, bring the nose up. Not super fast in terms of don't pull G's, but definitely work on getting the aircraft slowed down. And this is what I'm talking about here. Don't think about modifying your controls at all, even painting them. They are balanced. That's why, if you look at the preventive maintenance, it talks about painting is allowed except for control surfaces because they have to be balanced. And this is where you can find this in the Australia Flying magazine. Yeah, if you have a table like we saw in the gliders, follow it. Some aircraft do, especially outside of the US. If you're going above and beyond the design criteria, you're maybe looking for trouble. Turbocharging or bigger engines, terrific for reducing takeoff rolls and improving climb rate, but they may not necessarily be that great of an idea of climb or going fast at higher altitude. And, think about the age of the aircraft. We already mentioned this. It was only tested to 10% beyond redline V&E. And that aircraft has probably been out there and not brought back into standards for control surfaces and stuff ever since. So you want to think about that sort of stuff. Some things you can do practice-wise or learn about this. What can you do hands-on as a pilot is take a look at scenarios, especially in simulators, is really can work. Inadvertent IMC, where loss of control, recovery with it, high altitude. What are the things that can get you into trouble? Autopilot usage. When is it good? When is it not good? Also think about it as we're seeing this move into the general aviation fleet more and more, and this is going to become an issue associated with this, is speed hold and auto throttles. Is, you don't want to be exceeding the aircraft and flying it too fast with that. And, I showed the Eclipse earlier. That's one of the things in the certification on the Eclipse, we always had to do an emergency descent. And almost always that was at 10 or 9, 12,000 feet, roll it over, start the emergency descent. Okay, that's good, now recovered, and they passed their check rod. Then came the time where it had to do an emergency descent from up in the 20,000s and realized how hard it was not to overspeed the aircraft or lose control while doing a checklist, and realized, as someone that certified people in the aircraft, you really need the autopilot to be able to do that safely. That's not a hand-flown maneuver because the forces change dramatically so fast, so often in that. So, learn about the autopilot usage and practice when it's good, when it's bad. And recognizing steep spiral recognition and recovery. Inadvertent IMC for VFR pilots, for IFR pilots too, being practiced and proficient. And I mentioned two things here that I always have seen. It's so important that you know the proper procedure on what you should do first in terms of wings level, power reduction, power addition, that sort of thing, that people always seem to have trouble with. And then last but not least, I've seen this, and this has been in kind of the more advanced type training too, but dealing with other circumstances that end up leading to spiral recognition or spiral dive, and are they recognizing or recovering it? Incapacitated pilot or instructor. Have done some scenarios with that over the years where I literally have seen people completely lose control of the aircraft because they're so worried about the person in the seat beside them that they completely lose it, and ultimately in simulator scenarios would not only kill the person that was incapacitated and just had trouble breathing or something, but they killed themselves and the passengers on board. So, doing stuff like that. Glider pilots, hopefully, if you haven't heard of this, I talk to your instructor, but in the glider world, a good recovery procedure that works in a lot of gliders, but not all, is what's known as the benign spiral, which basically is opening your dive brakes and just letting go. We talked about it, rarely, especially if you had it trimmed properly, will the aircraft drop its nose beyond the 30 or 40 degrees with it, with the long elastic wings. You end up building up like this, especially with the dive brakes open, which are in the middle, so all the lift is being produced, and you end up with much more keel effect, dihedral is probably the better word to use with it. And it may wallow back and forth, but you can end up in a situation where, you know, you may not have any instrumentation, but if you got yourself caught in IMC conditions, that you could recover with it without exceeding the limitations of the aircraft. It's a personal note. I think we should add it to the practical test standards in ACS while take some other things out. But if you fly gliders, you know, I would strongly encourage you to talk to your instructor about that. And here's another part of this that is important. And you can take a look. We've done a program here in New England called Dealing with the Rogue Pilot. It's on the Boston FAASTeam YouTube channel. But, you know, some things with the aircraft, make sure it's not you, that's the rogue pilot, doing things that you shouldn't be doing. Like if you look closely at this picture of this Piper with it, is the airplanes are lasting way longer than we are as pilots, as humans. And you got to look out for the next generation. You know, think about it this way. You really are only the caretaker of your airplane right now. It's a very high likelihood that other people are going to be flying it after you. And it's probably even going to be some of your family members, a high likelihood of that too. So you want to make sure that you are not damaging your aircraft by exceeding the limitations on it and, you know, flying it past red line or whatever else. If you're flying aircraft that are used by multiple pilots, flying school, club, rental, whatever, I know there are some rogue pilots out there that are like, hey, y'all, watch this. And we just don't need that. You know, don't let others endanger you by horsing around in the aircraft you fly. You know, if you know of it, see it, hear it, whatever is, you know, report it immediately so that it can get checked. I mean, it's a personal suspicion, but having been involved enough in the industry over the years, I really do think some of the issues we've seen in some accidents may be factored by people doing stuff like that. And I even use this, one friend of mine who worked for an airline and interviewed, you know, was telling me he interviewed a well-known pilot one time. And, you know, it was quickly decided he was not going to hire him because, you know, the question was, well, tell me what you're most proud of in your aviation career. And the answer was, I've rolled every airplane I've ever flown, you know, no matter how it's certificated or whatever. And, you know, 172s all the way there. Okay, thanks, but we're done here. Type of thing. You don't want to be flying equipment being flown by rogue pilots like that. And that's a safety culture of your organization. You know, hopefully there's a good enough safety culture in your organization that they can handle it internally. But if not, you know, you do have your FAASTeam that you can start talking to at your local FSDO. Some of the stuff we've covered tonight is in the practical test standards. This is out of the commercial. You know, where we talked about performance with atmospheric conditions. Aerodynamics has been a big factor of here, and talking about, you know, exceeding airplane limitations and performance charts, tables, and all of that. So I hope you've learned some stuff here tonight. And to kind of finish off, just to give you a little review, here's some of the questions that I'm hoping you can start to answer and discuss as we leave off here tonight. When we talk about V&E, is it an indicated airspeed or a true airspeed? Or could it be both? You know, how or where can I find the true airspeed in my particular aircraft? Is it available to me as a pilot? Is it not? Do I have an old six-pack that maybe it's available, but I just don't know how to do that? Do I have a glass panel? And do I have that information available to me? What is flutter? Of course, that's probably a big one. What speeds does flutter usually happen at, or could it happen at? You know, what are some of the things that are designed in the aircraft I'm flying or you're flying to protect you in relation to flutter? Is it possible to exceed V&E with the airspeed indicator indicating below V&E on it? Go back to kind of question number one there and what we've talked about on flutters. What is some of the ways that maybe gliders protect against flutter at high air speeds. You know, who determines the limits for flutter on your home build? That's a good question. Did you design it? Did somebody else? How well do you think it has been done? Who were the people that designed it? Yeah. And why may more horsepower not be a good thing? You know, most pilots probably think that it is, but there may be circumstances with it. And then last but not least, which we're finishing off here with, is what is it that you can do as a pilot to increase your margins to make you safer now that you have some understanding of flutter and the impact of flying up near V&E. So do want to thank you. I hope, you know, this has helped with the FAASTeam. We always do strongly encourage that you do annual checking within an organization of some sort. If you don't have that, you can always use our wings program, but we want you to fly regularly with a CFI, work on practicing and doing it perfectly, and you can also document it in wings. And I do want to thank you. I mean, we've had a couple hundred of you here on tonight. I hope this information has been valuable. I hope that you've learned something. This is above and beyond just reviewing the fundamentals. I do know that, and I hope that you got something out of that. So I do want to thank you, and I look forward to seeing you again at one of our next upcoming New England FAASTeam events.